All right, so I covered this bug bounty write up in a stream several weeks ago, um, and a lot of people enjoyed walking through it. So I figured I would do kind of the start of what might end up being a bug bounty report read along. I think it'd be useful to kind of look at what reports are useful, what reports are written well, and I don't know. It helped me a ton to kind of understand what was going on in the bug bounty space. It was a really cool bug that we went over, and it was really well written. And I think it just kind of contained everything that a good bug bounty report should contain. So let's walk through it. So this one is from quite a while ago by Vinny Van. I'm going to zoom in a little bit to make the text a little bit more readable. So it is from 2018. It is a bug reported in Steam and other Valve games. And to give kind of an overview, basically there is a server explorer built into Steam and I believe just Valve games in general that allows you to get information about certain servers on different games. So I believe this one was exploiting Half-Life, but I believe or no, CSGO, I believe. But it affects basically all Valve games at that time, which is neat, like very cool. But basically, it's a buffer overflow in the server explorer that allows you to get RCE on anybody. And when I say anybody, basically, if you're able to convince somebody to pull up information about an exploiting server, so any server that is running this exploit, or if you're able to get somebody to click a link that will lead them to look up that information on that server, it leads to an RCE. They, I believe, popped calc in the video. So this gives kind of a brief introduction. And again, I don't want to even pretend like any of this research is mine. This is Vinny Van. Good rep on HackerOne, but this was reported in 2018, so quite a while ago. None of this research is mine. I just found the report and thought it was really good. In Steam and other Valve games, CSGO, Half-Life, TF2, there's a functionality to find game servers called the server browser. In order to retrieve the information about these servers, the server browser communicates with a specific UDP protocol called server queries. The protocol is well described in the online developer's manual of Steam, which I hear the developer manual for Steam is like super good. I haven't done any looking into it before myself, but it sounds like it's pretty good. We implemented a custom Python server, which only replies with the protocol using the same information available in the documentation. After a successful implementation of the protocol, we fuzzed several parameters and noticed that the Steam client crashed when receiving replies from our custom server. More specifically, the client crashed when we replied with a large player name used in the A2S_player response. When attaching a debugger, we noticed it crashed due to a stack-based buffer overflow. So basically what they did is they set up a game server using Python. And when I say game server, you can't actually play any games on it, but it is spoofing a game server using Python. And when somebody looks up information about that quote unquote game server, what the Steam client will show it as a game server. It's not, obviously, it's just a Python server running, the exploit code, but it will return a response that in the A2S_player field has a large string. I think we're going to talk about it here in a second, a large Unicode string. And that large string is parsed by the Steam client in a way that is unsecure and can lead to a buffer overflow and then an RCE, which they will kind of explain the exploitation later. So let's talk a little bit about the exploit. We wanted to prove impact and build an exploit. First, we tested it on Linux, and we were able to control the execution flow instantly by overwriting the return address. However, on Linux, we were able to control 2 bytes of the EIP register only. So just that portion of the EIP register, and we didn't explore it further. On OS X, the process terminated with a sig abrupt or sig abort, which means that there's probably canary protection in the library on OS X. Then we tried to exploit it on Windows, and we were successful. Tested on 8.1 and 10. So here is the first, the whole first section was written well. The second impressive thing here is they tested it on 3 different operating systems. A lot of bug bounty reports that I've seen only test on Windows. Sometimes there's reason there, like it's just a Windows only app. but they went above and beyond and tested it on 3 different operating systems and gave specific information about what happens with those 3 operating systems. On Windows, sending a player name via UDP like A times 1100, so 1100 A's, would result in the following stack layout. And then it gives 25 bytes of code here. We're not going to view all of that, but yeah. This happens due to Unicode conversion, Widecar, because player names can use Unicode characters. Sending a player name with a Unicode character like U/U4141 1100 times will result in the following layout. So you get to control the entire byte if you do it that way. However, since we were corrupting the stack and registers before the function returns, we had no control over the EIP register yet. The program was crashing after dereferencing the EDI register, but we had control over it. We satisfied these special conditions using constant values present in the Steam.exe library. Or binary, sorry. So basically, they only had control over the EDI. You really want control over the EIP. The EIP is what actually tells, or what is actually pointing to the current, the current instruction. So if you're able to overwrite the EIP register and get it to hop somewhere else in memory, then you can cause it to hop to your own code. Here, they only have control over the EDI register, which is, I believe, just a general register. So they don't have very interesting control at that point. That said, if they are able to manipulate the EDI register in a way that allows them to eventually overtake or eventually control the EIP register, which is what they ended up doing, then that's interesting control over the binary. Then we built a Unicode ROP chain with gadgets from Steam.exe only to call virtual protect dynamically to make the stack executable and jump to our Unicode shellcode to execute command.exe. So basically what that's saying is ROP is its own thing. What's his name? Really good security YouTuber. Let me look at my subscriptions. He did a great video that I'll link to later on ROP. Let me look it up. It's called ROP is Dead. It's dead. Right there. John Hammond. God, why did I forget his name? ROP is Dead. I will pull up the video here. Very, very good video. Highly recommend it. Where he talks about ROP programming or ROP exploitation, specifically. Let me pull that back up. So I would highly recommend watching that video if you want to kind of understand ROP a little bit better. I'm not going to explain it here because, frankly, I need to do more research on it myself. So they used ROP gadgets, which is basically a way of kind of getting the program to hop around in a predictable way to get to their own code, then called virtual protect to basically make the stack, the area of stack in memory executable. The stack holds the actual shellcode itself, so they want to make that executable so that they can actually initiate their shellcode. This was a big challenge since we couldn't use values like that in our ROP chain, otherwise the string would be terminated, and we couldn't use invalid Unicode characters like that because the library represents them with a question mark. So obviously there are lots of interesting cases where normally ROP would work, or normally the shell code that they were creating, not ROP, but normally the shell code that they were creating, they could use certain characters, but they couldn't use them because of the unique context in which they were creating the shell code. Basically, if they were using this specific string right here that ended in 40, that would terminate the string. So obviously that's not what they want to do. They want to terminate the string in the middle of their shellcode. We couldn't use invalid Unicode characters like that because the library would replace those invalid Unicode characters with question marks. Again, not useful. Everything is calculated using the Steam.exe base address. This address changes if you restart your Windows 8 or Windows 10, not if you relaunch Steam. So basically, that is ASLR. And what ASLR, I almost said DSLR, which is a camera type. ASLR, which is address space layout randomization, is going to change the base address of the executable every time your system is restarted, not when the executable itself is restarted. So basically, if I ran this exploit, it worked, and then I closed Steam out and then opened it again and tried to connect to that same exploit server again, it would have the same exact base address, so it would still work. The exploit is 100% reliable if you edit the base address on the exploit, but you can't predict the base address in the computer of a victim due to ASLR. However, we have two exploit scenarios. Only 9 bits are randomized. An attacker can successfully exploit a victim with a probability of 0.2%, which is more than enough if we were talking about an attacker distributing this exploit massively to all Steam users. So what that's going to mean if they randomly guess the base address of steam.exe and they throw this server up, if you have like hundreds of thousands of people who are potentially trying to connect to this exploit server, which is realistic since Steam is so widely used and these Valve games are so widely played, then you're going to still get quite a few people just by like random. And then the vulnerability can be changed with another memory leak vulnerability to make it 100% reliable. So those are two circumstances where the base address changing doesn't really matter. So then they give the steps to reproduce. Now, obviously, I'm not going to say obviously, that might be rude, but this exploit is from 2018. It's not going to work again in the current version of Steam and with, the current version of these games. So they're doing this walkthrough to reproduce it for the version of Steam that was around back in 2018. So here you've got videos for the POC. Another huge props to them, like having the videos themselves of them exploiting this. So you'll see they'll go to servers, they'll find the server that they are running, and they'll view the server info, and that pops command.exe. So this is proving RCE. This payload that was sent popped command.exe on another computer. Damn it. So that made me scroll all the way back up. So let's scroll down. Now this is where it gets interesting. If you send somebody a specifically crafted link and they click it and they have Steam installed, then it's going to also run the exploit. So that I found really cool. Like you don't even have to view it within the Steam Explorer. You can just open that specific link. So here it's actually a hidden iframe. So that hidden iframe is then going to run Steam, open up that server Explorer. That's going to retrieve the payload, and you'll see it here in a second running the exploit. Again, wicked cool. This means that you don't have to run that server Explorer and connect to that specific server that's running the exploit. You can just click a link or end up on a page with a bad iframe, and that's going to do it all the same. And again, let's scroll all the way back down. Another huge props. They've got the exploit POC here for anybody. Basically, while when this was just in Steam's hands or just in Valve's hands, that they were able to literally copy and paste this exploit, run it themselves, and test it. So that's rad. Then they explain impacts. We've already kind of talked about this a little bit, so I'm not going to rehash all of it. It's also already a long video. But basically they're saying an attacker can execute arbitrary code on the computer of any Steam user who views the server info of our malicious server. Literally anybody. Usually an attacker would initiate a backdoor connection to C2 infrastructure to gain access to the computer of the victim. From there on, they can do what they want. So, several points to be made here. First off, fantastically written. Just a very well-written report. They also give props to their co-author. Really cool. They ended up making $18,000 from this RCE. I think that's a little low. Like an RCE with such trivial exploitability against any Steam user, like I would think that'd make a lot more money, but this was 4 years ago. So, there may be some excuse there. That said, the report was incredibly well written, including the POC code is awesome. The way that they walk through everything to include impact, to explain it to the people who wrote the software and are trying to fix it, that's awesome. Just a really well-written report. I'll include a link to it in the description so that other people can read over it. It's a really well-written report. If you enjoy these bug bounty walkthrough videos, feel free to let me know. This took a little bit to produce, but I learned a lot from the report, so I've got to give props, and I think it helps, with my research as well. So if you enjoyed it, let me know. Take it easy. Peace.